Two bottles of crystal clear drinking water sit before you. One is perfectly safe, the other contaminated with invisible radioactive particles. No smell, no color, no taste, yet one could pose a serious threat to your health. So, how do we detect something so dangerous that hides in plain sight? In this video, we're diving into nuclear science to uncover how scientists and engineers detect radioactive particles in the drinking water that surrounds us. Let's break down how this cutting-edge detection process works and why it's so important for our everyday lives. First, let's talk about radioactivity in water. Radioactive substances like uranium, radium, and thorium occur naturally in rocks and soil. Over time, these can leach into groundwater and surface water, which is a source for our drinking water. When these elements break down, they emit radiation in the form of alpha and beta particles. This process is known as radioactive decay. If radioactive particles are present in water, they can be harmful if consumed over long periods of time. But how can we tell if they're present? There are two types of radiation we typically test for in water: alpha and beta radiation. Alpha particles are made up of 2 protons and 2 neutrons, which makes them heavy and highly charged. They don't travel far and can't even penetrate human skin, but if ingested, they can cause damage to internal tissues. Beta particles, on the other hand, are much smaller and lighter, just electrons or positrons. They can travel further than alpha particles and can penetrate deeper into materials, including our bodies. Detecting both types in drinking water is essential to ensuring its safety. As complicated as this may sound, it can all be detected using a special instrument. To measure the levels of radioactivity in water, we use a device called a gross alpha-beta counter. But what does gross mean? It simply means we're testing the total alpha or beta activity without identifying specific radionuclides, giving us a general idea of the water's radioactive content. Let's explore the gross alpha-beta counter. First, let's look at the control panel located on the front of the instrument. All of the buttons are manually control the autosampler unit. This panel connected to the electronic board below, allowing to control the movement of samples in and out of the chamber and restack all the samples once the counting process is complete. However, this manual controller is primarily used for maintenance purposes, as regular counting operations are managed by specialized software displayed on the monitor. Right behind it, there are 2 towers on the left and right function as autosamplers. These autosamplers improve efficiency by automating the process of placing multiple samples into the detection chamber, enabling the system to handle large volumes of samples without the need for constant human intervention. This speeds up the workflow, especially in laboratories handling numerous samples. We will explore this further later. Under the top cover, there is a lead shield surrounding the detection chamber to block any background radiation from the environment. This ensures that only the radiation emitted from the sample itself is measured, making the readings more accurate by minimizing interference from external sources. Without shielding, radiation from the environment like cosmic rays could cause false readings, making the instrument less accurate. Inside the shielded chamber lies a gas proportional detector, the core component of the device, responsible for detecting alpha and beta particles emitted by the sample. The detector contains a gas chamber filled with a special inert gas mixture of methane and argon. The gas enters through side inlets and exits through outlets. When the drinking water sample containing radioactive material is placed under the detector, it emits alpha or beta particles. These particles enter the gas-filled detector through a thin window that allows radiation to pass through while blocking unwanted particles. Let's take a closer look inside the gas chamber. Upon entering the chamber, the alpha or beta particles collide with gas molecules, transferring their energy and causing ionization. This process knocks apart gas molecules, producing positively charged gas ions and free electrons. The anode wire and cathode are essential for creating an electric field inside the gas chamber and collecting the charges generated by ionizing radiation. The anode is typically a thin wire placed along the central axis of the cylindrical chamber, while the cathode is formed by the chamber's inner surface. A high voltage is applied across these electrodes, creating an electric field inside the detector. In this field, free electrons, negatively charged, are drawn toward the positively charged anode, while the positively charged gas ions are attracted to the negatively charged cathode. As the electrons move toward the anode, they accelerate due to the electric field. In the proportional region, if the electric field is strong enough, the electrons gain sufficient energy to ionize additional gas molecules along their path, creating more ion pairs. The movement of these ions generates a small electrical pulse proportional to the energy of the detected radiation. This phenomenon is known as the avalanche effect or gas amplification. This pulse is then amplified and analyzed to distinguish between alpha and beta particles, and the results are displayed, indicating both the radiation level and the type of particles detected. Up to this point, we have thoroughly explored the detector. Let's put the detector back in its place. Now, we will go back to our drinking water sample to see how to prepare it. First, a specific volume of drinking water is collected. The sample is transferred to a beaker and placed on a hot plate. The water slowly evaporates over 2 to 3 days, leaving a small residue that concentrates any radioactive particles. The residue is carefully placed onto a small stainless steel tray, or planchet, and positioned under an infrared lamp. This transfer process uses a dropper and is repeated until all of the concentrated residue in the beaker is completely dry. This step ensures that any radiation present in the water is sufficiently concentrated for detection. It's important to note that the sample needs to be handled carefully since we are concentrating radioactive material. Once it's ready, we can move on to detection. The sample is placed into a sample holder of an auto-sampler unit. Each carrier is identified by an alphabet code, which corresponds to a pre-selected batch group and procedure. After loading all samples, counting is initiated through software displayed on the monitor. Just below the carrier track, a roller mechanism moves the carriers through a scanner for verification. The sample is then pushed into the chamber to begin the counting process. After the instrument runs its counting process, it generates a count per minute or CPM result. This tells us how many radioactive particles the detector picked up in a given time. These results are then compared against safety standards to determine if the water is safe to drink. Regulatory agencies like the Environmental Protection Agency, EPA, in the US, and similar agencies worldwide, have strict guidelines for how much radiation is acceptable in drinking water. For example, the EPA has set a maximum contaminant level of 15 picocuries per liter for alpha emitters and 4 millirems per year for beta emitters in drinking water. And that's how we use a gross alpha-beta counter to detect radioactivity in drinking water. This amazing technology is crucial for our health and safety. Thanks for watching. If you learned something new today, be sure to like this video and subscribe for more informative, casual learning content. See you in the next video.